Hello again. So, we have finished looking at in the last lecture on how to deal with periodic loading. So, till now we have been looking at loads which are essentially there for very long duration. In other words, we know we only consider a situation where the loading is there. For example, harmonic loading, only thing that we say is that a harmonic load is a time period, but then the number of cycles we know goes on forever. Similarly, for periodic load also we say that we do not know when it started and we do not know when it ends. We are just taking a particular period during the time, taking a window. Today, we are going to start looking at something that is known as pulse loading. Pulse loading is essentially a short duration load. In other words, the loading starts at a specific time and ends at a specific time. And what are pulse loads? These are typically, what do we mean by short duration loads? Short duration essentially implies that if I call T d as the duration of the pulse, this is of the same order of magnitude as the time period of the structure. When I say same order of magnitude, I essentially mean that they are similar to each other. It is not as if that T d is equal to T, it just means that T d could be T by 2, could be T by 4, could be 2 T, but not more than 2 T for sure. So, if we say that, then what happens? Let us look at it. So, let me take and here what I am going to look at is, we are going to look at mathematically defined loads, so that we can get closed form solutions. And let us start off with the simplest kind of load, and that is a rectangular pulse. So, this is starts at 0, this ends at T d. The loading is P 0. So, essentially it starts at 0, and it is P naught till T d, and then at T d it goes to 0. Obviously, the rise and the fall are instantaneous. This is a mathematical abstraction. In reality, all we say is that the rise and fall are very short compared to the time duration. So, in other words, P of t is equal to P 0 between 0 and T d, and 0 for t less than 0 and t greater than T d. So, now the question becomes, well, how do we solve this problem? Well, immediately there is no difference in the, we know how to solve any partial differential equation, we know all of that, but there are two interesting aspects to this problem. One, that I have to solve, this is a two phase problem. Phase 1 and phase 2. Phase 1 is known as during the period when the loading is non-zero, and phase 2 is after the duration of the load, we have what is known as a free vibration phase. So, this is a forced vibration, and this is free vibration. So, now let us look at this particular problem. So, here what we are going to do is, we are going to solve for this rectangular pulse, we are going to solve both the phase 1 and phase 2 problems. And note that again our sole interest here is in getting the peak value of the response. That is all we are interested in, because we are not interested in the time duration. Okay? Now, interestingly enough, one particular point that requires, and this we saw when we were looking at damping. Remember, when I was looking at free vibration, I said that damping takes some time to start off, okay? And that viscous damping, after 1 or 2 cycles of vibration, that is only the time when viscous damping takes off. Now, since T d is of the same order as T, you are not going to get 2 cycles of vibration at all. Okay? So, for all practical purposes, we can solve this problem as an undamped problem, okay, both for the forced vibration and free vibration, because again understand, we are not interested in the time history at all. We are interested only in the peak value. Why? Because the peak value is what we need to design a structure for it. Okay? So, let us now look at it. So, the problem is no longer the solution of m u double dot plus C u, but we can drop the C u term. Why? Not because C u is 0, but because the viscous damping takes time to happen and T d is not sufficiently long enough for the loading to happen. Okay? So, this is the problem that we solve, and the problem here is one of, now note that since it is a short duration load, u 0, that is, and u dot 0, which are what? Initial displacement, initial velocity. These are important, and we will solve the problem as a. So, I am looking at phase 1 solution right now. Okay? So, how do I solve it? Particular solution is P naught upon k, and the homogeneous solution is, well, u is equal to A sin omega t plus B cosine omega t plus P naught upon k, and A and B I get from here. Okay. So, if you look at it, if I differentiate it, okay, u dot is equal to A omega cosine omega t plus minus B omega sin omega t, and the plus, note that this is a constant. So, differentiation is 0. Okay. So, if we put u 0, since sin omega t equals 0 is 0, what we get is B cosine omega t plus P naught upon k is equal to 0, and this cosine omega t is 1. So, we get that B is equal to minus P naught upon k, and again if we took u dot 0 is equal to A omega, which is equal to 0. This implies that A equal to 0. This implies that u of t is equal to P naught upon k into 1 minus cosine omega t. So, this is the solution of the problem. Okay. And again, there is a reason why I am writing down u dot of t, and this is equal to P naught omega upon k into sin omega t. Okay. So, this is the solution. Okay. Now, note that this solution means what? Okay. Let us look at it, and that is that we have a situation where phase 1 is u of t is equal to p naught upon k into 1 minus cosine. Let us look at phase 2. Phase 2 is what? Well, let me put down u dot t also here is equal to p naught omega k sin omega t. Okay. So, now if we put this together, what do we get? We get it the following. Phase 2 basically becomes a problem of mu dot plus k u is equal to 0. Why? Because essentially you have a situation where again we are looking only at the peak value. So, the peak value will happen in the first 1 or 2 cycles. So, damping does not come into picture. So, this we know the solution to. This solution is, and where you have u of T d and u dot of T d as the initial conditions. So, then I can write, I know the solution to this. This if I just put it shift from T d, then this solution basically becomes u dot T d upon omega into sin omega t plus u T d cosine omega t. Again, the value itself is irrelevant. So, what we want is we only want the peak value. So, the u peak is equal to u T d squared plus omega the whole square. So, that is the peak value. Okay. In phase 2, this is the peak value. So, I can plug in, these are my responses. So, I can plug those in, and if I take p naught upon k outside, I get u dot T d is this plus whole squared. So, this basically becomes 1 minus 2 cosine omega t plus cosine squared omega t, and u upon omega. So, this omega again p naught goes. So, this becomes plus sine squared omega T d. That is the peak value. So, if I look at this, this becomes 1. So, it becomes 2 minus square root. So, if I look at that particular solution, this is 1. So, it becomes 2 minus 2 cosine squared. So, this becomes, peak value becomes u p is equal to p naught upon k 2 minus 2 cosine omega d t squared. So, this is equal to, from trigonometric equality, this becomes 2 p naught upon k into sine. Now, it becomes omega upon 2 sine omega upon 2. So, omega is 2 pi upon t. So, this becomes sine pi T d upon t. So, that means if this is the peak value, right? Okay, let me just write this down. So, the peak value in phase 2 is equal to 2 p naught upon k into sine pi T d by t. And if I rewrite this as dynamic factor, then this is 2 sine pi T d upon t. Okay. This basically comes from the fact that this into this essentially becomes 2 times 1 minus cosine omega is equal to sine squared pi omega T d upon 2. So, that is where this becomes square root of sine squared becomes the 2 here, and so it becomes 2. So, it becomes 4, square root of 4 is 2, and so this is what it comes out. Okay. So, this is the dynamic amplification factor if peak is in phase 2. Now, let us look at phase 1. Okay. Suppose when will now let us look at the phase 1 displacement. Understand that for the maximum to occur in phase 1, this has to be equal to 0. Do you understand that? Okay. So, I am going to write the following, and that is that we have a situation where the peak value for the peak to lie in phase 1, okay, P naught omega upon k into sine omega t is equal to 0, and omega is what? Omega is equal to so, now note that for this to be equal to 0, since these cannot be 0, this has to be equal to 0. So, in other words, let me rewrite this sine 2 pi t upon t is equal to 0. So, what does that mean? This implies that your 2 pi t upon t is equal to, let us look at it. What does 0 imply? 0 can be, well, it can't be 0 because t equal to 0 is a trivial solution. Okay. So, it has to be, what is the next one? It is n pi. Okay. Now, obviously, now the duration is small. So, which is the first one? So, in other words, if T d by t is greater than, no, n pi, the first one is pi upon 2 pi is half. So, if T d by t is greater than half, then peak can occur in phase 1. And what is that peak then? Well, 2 pi upon t. So, omega t is equal to pi. So, if I take omega t is equal to pi, look at this. This is cosine omega t. So, cosine of pi, what is cosine of pi? Minus 1. So, this becomes 2. So, your u peak is equal to 2 p naught upon k. Okay. So, this implies that if T d is greater than half, then peak can occur, and this is the peak. However, if T d by t is less than half, peak in phase 2, and what is that peak value? The peak value is equal to, so in other words, d is equal to 2, and if peak is in phase 2, d is equal to 2 sine pi T d upon t. Note very interestingly that if T d by t is equal to half, then where does the peak occur? If T d by t equal to half, then the peak occurs at t equal to t d, and what is the value? Put t d equal to t here, what do you get? Sin pi. Sin pi is what? Sorry, I made a mistake here. Yeah, it is. Okay. Yeah, if t d by t is equal to half, this is sin pi by 2. Sin pi by 2 is 1. So, d is equal to 2. So, it exactly is d equal to 2. So, that means what we have is, if t d by t is greater than or equal to half, d is equal to 2, and if t d is less than half, then d is equal to this. So, we have solved the problem of the peak, and if you look at this here, you look at this one, okay, this one is a sinusoidal function, which is this sinusoidal function, okay, goes here at t d upon t equal to half, okay, it is 2, which is what we get here, okay, and after that, if it is longer duration, then t d is equal to 2, which is what we get here. Okay. So, this one, you look at it, this is what is known as the shock spectrum for a rectangular load. So, shock spectrum, essentially if I give you this, okay, if you know t d, the duration of the load of a rectangular load, and you know t, okay, you just go here, read it off, and that gives you the dynamic amplification factor, and multiply that by P naught upon k, and you have your response. So, in other words, the shock spectrum, replaces, I've done the mathematics here, over here I have done the mathematics, but if I had this, I did not need the mathematics. This shock spectrum, if someone gave me the shock spectrum, I could then look at it and say, oh, okay, this is my duration, look at it, read it, that is the duration. So, shock spectrum actually gives you a full idea about how to go about it. So, now I will just do another specific duration, short duration load before I move on to some other kind of loading, interesting loading that you can do, and that is, let us look at the short duration load. Another kind of short duration load is the one that I have drawn here, which is known as the half sine curve. Okay. So, let us try to get this shock spectrum from our mathematics. Okay. So, what is the half sine? Half sine is essentially this, where this is duration, this is this, and this is given as, so this is P naught. So, P t is equal to this is P of t. P of t is equal to P naught sin pi t upon T d for 0 less than and is equal to 0 for t less than 0 and t greater than T d. This is my half sine pulse. Okay. So, now how do I solve for this? Well, again I go through the same step, solve the phase 1 solution, and phase 1 solution for phase 1 is basically 0 T d this. Actually, in this particular case we can do this, and the solution, and of course, we have the fact that u 0 is equal to u dot 0 is equal to 0 at rest initial conditions, and therefore, u of t is equal to, and again I am solving what? The undamped problem. So, the undamped problem becomes a sin omega t plus b cosine omega t plus the solution of this. The solution of this is nothing but, if I put this in and solve this thing, I already know what this is. This is equal to plus P naught upon k into 1 minus beta squared. Beta squared is omega, now omega is what? Pi upon T d is omega upon omega, which is 2 pi. So, this becomes what? It becomes T by T d squared. So, I am going to put this as 1 over 4, because I have, remember, this pi upon 2 d and the other one is 2 pi. So, omega bar is pi upon 2 T d, and omega is equal to 2 pi, pi upon T d. Omega bar is pi upon T d and omega bar is 2 pi upon T. So, beta is equal to pi upon T d upon omega, omega bar upon omega. So, this becomes then T upon 2 pi, pi cancels, it becomes 2. So, this is what it has, and then into sin pi by T T d. This is my solution of the first equation, and I can solve for A1 and A2. If I solve for A1 and A2, I get that B is equal to 0, and because note that if I put t equal to 0, this one becomes B, this goes to 0, this goes to 0. So, therefore, B is equal to 0. I mean, u 0 equal to 0 implies that B is equal to 0, and from u dot equal to 0, I get that A1 is equal to minus T by 2 d into P naught by k upon 1 minus, and I am going to take this inside, T upon 2 d the whole squared. So, this is A1, and so therefore, if I look at the total solution, this becomes the following, right. I am just now going to substitute A1 here and take out the P naught upon k outside. So, this is going to be equal to u of t is equal to P naught upon k, and then note that I have 1 upon 1 minus t upon 2 d. This is 1 minus beta square. We have already solved this, so I am not going to solve it again. So, that one also comes out. So, inside I have what? I have sin pi t upon t d minus t upon 2 d into sin 2 pi by t. And again, this 2 pi by t can be actually written as T d upon t sin pi, anyway, it does not matter. Let me not confuse the issue here. So, this is the solution in phase 1 for a half sine pulse. And once we have that, I can actually get u dot also. U dot turns out to be equal to, well, it is easy to do, P naught upon k, and I will get, so I will get pi upon T d, and pi upon T d. So, that is 1, so that is cosine pi t upon t d minus cosine of 2 pi t upon t. Okay? So, this is what I get as my solution for the equation. Okay? So, now let me first start off by, so we've why did I do the u dot t in the second phase? Well, that's because, I mean, sorry, in the first phase, because if maximum is in phase 1, then this has to be equal to 0. Okay? And if this is equal to 0, I am sorry, there is this 1 minus t upon 2 d, this is still there. Okay? And so, over here what you have is, so I get cosine pi t upon t d minus cosine 2 pi t upon t has to be equal to 0. That is the obvious thing that you will end up getting, and in other words, so note that for this to happen, this has to be equal to this, because this minus this. So, this has to be equal to this. So, if this has to be equal to this, all that it means is that pi t upon t d is equal to 2 pi n plus or minus, sorry, this is the one. So, I am just, this is wrong, this is not correct. What you get is this one comes on this side. So, it is basically what you are getting is t 2 pi t is equal to pi t upon t d plus or minus plus 2 pi n. And note that this one will this is valid for the first n. So, it is 2 pi. So, if I do that, I get 2 pi t upon t is equal to pi t upon t d plus 2 pi. So, then I get this side to be coming in, okay, and I can solve for t. I can solve for t over here. Okay. So, anyway, I mean, this is neither here nor there. This one I need to solve this for time t depending on my t d and t. Okay. So, this is the time at which I have the peak, and then that one I plug back into here, and I will be able to get the peak value of the displacement. Okay. So, I am not going to substitute all of those, but so this becomes a little bit more complex. So, if you look at this, okay, this one does not follow as clean a line as we got for the other one, right. It is a much more complex solution. Okay. Now, the question then becomes that can I substitute in here. So, I can just put over here, and I can just take out the pi, and I get t upon t is equal to, sorry, 2 t, no, let us make it t upon t is equal to t by 2 t d, okay, plus sorry, this 2 pi is gone because I so plus 1, okay, minus. So, if I take this in, I get t upon t plus t upon 2 dt is equal to 1, and therefore, I can just say that t into 1 plus t plus 1 by 2 t is equal to 1. Okay. So, that's I am sorry, that's what we get here, and I can solve for t by saying that look, t is equal to 1 upon 1 plus t upon 1 plus 2 d. So, now depending on the omega and time duration and the time period, we can compute the time at which this happens, and then you plug this in here and you will get it. Okay. So, that is when it happens in phase 1. Okay. Now, the question comes that what happens in phase 2? Well, let us see what happens in phase 2. In phase 2, okay, what are we know that it is going to be u max is equal to u t d squared plus u dot t d upon omega the whole square. So, we have to do this. So, we have to find out what u of t d is. So, u of t d substituting into that becomes p naught upon k 1 minus t upon 2 t d the whole squared into now sine of pi, because t is equal to t d. So, t upon t d is 1 sine of pi minus t upon 2 t d into sine. Now, you see this is equal to 2 pi t d upon t. Okay. So, sine of pi is, what is sine of pi? 0. So, what we get is u of t d is equal to minus p naught by k into t upon 2 t d all over 1 minus t of 2 t d squared into sine 2 pi t d by t. This is u of t d, and similarly substituting in here, what we get it as is, if I put t d, t is equal to t d, this becomes cos pi and this becomes cosine t d upon t. So, this essentially, if I substitute that, u dot of t d is equal to p naught upon k, okay, pi by t d, okay, upon 1 minus t upon 2 t d the whole squared, okay, into cosine of pi. What is cosine of pi? Minus 1, and so therefore, cosine of pi is minus 1, sorry, cosine of 0 is 0, cosine of pi is 1, sorry, it is 1. So, therefore, what we get is cosine of pi is 1 minus cosine of 2 pi t d upon t. Okay. So, that is what we get. Okay. Sorry, I am making a mistake here. Cosine of pi is minus 1. I am very sorry. I am extremely sorry. Cosine of pi is minus 1. So, it is minus 1 here and minus here. Okay. So, ud and utd is this. So, now if I write this up, it's getting fairly complex, but just stay with me. What you get is, if I do u dot squared, okay, and u dot is divided by omega. So, let me see what I get as u td by omega implies actually u dot t d into t upon 2 pi. So, essentially if I put this in here upon omega, this becomes essentially t upon 2 pi. So, this becomes again t upon 2 t d. Okay. So, therefore, essentially what you get is u max in phase 2 is equal to, you have got, I am going to take the entire P naught upon k into 1 upon 1 minus t upon 2 d the whole squared. I am going to keep this entirely outside, and inside what I have is the following. I have sine squared 2 pi t d upon t, and over here multiplying this into t upon 2 d the whole squared, t upon 2 t d the whole squared. Okay. And on this side I have minus minus, so I get plus 1 plus cosine 2 pi t d upon t the whole squared, and inside I have t upon 2 t d the whole squared. Again, this is there in both of them, so I can take that out. So, this becomes again P naught upon k, I will put t upon 2 t d outside, inside 1 minus t minus 2 t d squared, and inside I have 1 plus cosine 2 cosine 2 t d by t, and then plus cosine squared 2 pi t d by d plus sine squared 2 pi t d by t. These two become 1. So, this becomes, and then of course, square root, I forgot the square root here, okay, is equal to P naught upon k into t upon 2 t 1 minus t upon 2 t d squared, okay, then into 2 plus 2 cosine 2 pi x t d square root. This becomes, if you look at it, this becomes 2 cosine of it becomes 2 into 2 cosine squared pi t d upon t x, and so if I do the square root of that, this becomes equal to P naught upon k into t upon 2 t 1 minus, and the 2 comes out. So, I have essentially I will just rewrite it, t upon 2 t d whole squared multiplied by 2, the 2 into 2 4 comes out, square root is 2, and the square root of cosine squared is cosine of pi d upon t. this is your u max if max is in phase 2. Now, in the other case we got a beautiful situation where we could find out a value of t upon Td or Td upon T. Okay. Remember in rectangular, if Td upon T is less than half, it is in phase 2 and we know the value. Okay. And if Td upon T is greater than half, then D is equal to 2. Here, if you note that you can't really do that purely because this process this is the t at which ut is maximum. Getting this is a fairly complex process. So, what we do is, how do we solve this problem? How do I plot this red curve which is for the half sine wave? Well, the easiest thing is, I know that at any time Td upon T, I solve this. This I can solve. Given Td upon T, I can solve for this and get, of course, u max upon P naught upon k. That gives me the dynamic amplification. This is completely dependent on Td by T. For a particular value, I know what this value is. So, this is the maximum if it occurs in phase 2. Then, for the same Td by T, I can solve for this one. Okay? So, if I solve for this one, okay, this one essentially becomes something like, I could rewrite this in this form, that T is equal to 1 upon T into 1 plus okay. So, note that this time duration does not only depend upon Td by T, it also depends on T itself. So, therefore, this max will occur at different times for different Tds. Okay, it's Td by T. So, therefore, all you need to do is find out this for a given Td by T, find out this for a given Td by T and of course, time, you know that you get this T, and for that T substitute into this and get the dynamic amplification, which is ut upon P naught, okay, u max, by substituting that T in here and get that value and compare this value with that value. Whichever is the what will it be? Whichever is the larger value is the one that is operational. Typically when you are very, very low, okay, when you are very, very low, very, very small, this operates, because when Td by T is very much less than 1, then it does not get a chance to do this. Okay. And therefore, since it does not get a chance to do this one, it will always be this. So, if you look at this particular part, for a small part, it is this. But once Td by T becomes slightly larger, then what happens? Then you have to compare this and this, because of the solution, that this solution does not only depend on Td by T, it also depends on T itself. Okay. So, that is the reason why you find out both, whichever is maximum is the value that you get. Okay. So much for this, and similarly what we can do is, if we come here, okay, we have drawn another curve for a symmetrical triangular. Symmetrical triangular is typically of this form. I will just show it to you. A symmetrical triangular is, I am not solving this, I will leave it up to you to solve it if you wish to. P of T, T, symmetrical triangular is Td, Td by 2, P naught. Why don't you people, you take this as an exercise. Take this as an exercise and find out this, show that this is the shock spectrum for a symmetrical triangular one. Okay. Of course, again for this also, you know, the TD by T value for which it is in phase 1 and phase 2 is not obvious. Of course, in the smaller part it will be in phase 1, that's known for sure, because when TD by T is very small, the duration of the load is not large enough for it to be occurring in phase 1. So, this area is always in phase 2. However, just like in this case we had half, in this case we did not know when it was coming, in this case also it is going to be slightly problematic, but you can plot it. You can put in values of TD by T and you can get it. Okay. So, that is what is known as pulse load. I have shown you that in pulse load, short duration loads, you do not only have one solution like we used to have for harmonic and periodic, you have phase 1 solution, phase 2 solution, and how to compute the peak. I also showed you. For the rectangular, we knew exactly when it will occur in phase 1 and when it will occur in phase 2. For the half sine, I showed you, well, for phase 2 you can get a closed form solution. For phase 1 it's not a closed form solution for the peak value, and so you do not know where it is. However, the point that I am trying to make is that you do not have to solve anything, any mathematical solution. If you are given the shock spectrum and you are given the particular kind of load, if you know what kind of load you have, you can always read off here. TD upon 0.75, read 1.5. If it is symmetrical triangular, this is the value. You just need that and multiply it by P naught upon K, and you have your peak response. That is all you need. So, the shock spectrum actually is very, very useful for pulse loads where you do not have to solve any problem. Okay? Thank you very much. See you next time. Bye.